Luke Bouma, sorry, from Caltech, talking about co-rotating glass gas. Thank you.
Thank you. My name is Luke Bouma, and I'd like to start by requesting your active participation. So you might need to look up from the laptops. I'd like you to please raise your hand if you have a good guess for what explains the sharp features in this light curve. If you know, please raise your hand. Oh, come on. All right. So these are two stars passing in front of each other. Now, same question, slightly different light curve. I'd like you to please raise your hand if, in this case, you know what explains the smooth features in this light curve of AB Doradus. Face folded looks something like this. Okay, maybe slightly fewer. So this is a spotted star. It rotates every 12 hours. The spots cause the brightness fluctuations. Now, you're all doing pretty well. I'm going to make it just a little bit harder. So this light curve, at first glance, looks like a total mess. But if you look closely, if you phase fold, yeah, what? Okay, show of hands. I'm not going to ask if you understand what explains this, but I'll ask, have you ever seen anything like this? If you have, please raise your hand. Nice, cool stars, doing pretty well. Okay, so what I'd like to talk about today, now that we've demonstrated that stars like this exist, is a little bit about why they exist, and also maybe why now is a good time to be thinking about them. Now, these complex periodic variables are actually not that rare anymore. We know of about 100 objects like this. And they have a common set of characteristics. Okay, they all spin fast, periods below 2 days. They all have ages below 200 million years. They're all low mass stars, masses below about 40% that of the sun. They comprise about 1% of observed young stars. The fraction's a little bit higher for the youngest stars. It's a little bit lower for the oldest. Now, that seems like it's kind of rare, but transiting planets exist around 1% of stars because there's a geometric requirement to see the phenomenon edge on. If that applies to these objects, then they could be more common by perhaps an order of magnitude. Two other important observations. The first is that the sharp features in the light curves have been observed from ground-based photometry to be chromatic. They're deeper in the blue than they are in the red. And, very important, there is no evidence for disks in these systems. Not from the infrared excess, not from spectroscopy that's been acquired. As a tangential point, please do not call them dippers. That is a different class of object. Now, the pioneering work on these objects was done going back to the K2 days by Louisa Ribol, sitting over there, and by John Stauffer, who has been instrumental in the history of this conference series. Ever since those original studies, the picture that's been presented, a little bit different here. This is AI generated, so take it with a grain of salt. But the picture that's been generated is one where there's co-rotating circumstellar material. All right, and today, I basically agree with this picture, but what I'd like to provide is a little bit more nuance. In particular, I think what we can say we're seeing is transient co-rotating gas clumps around these stars. So just so that we're all on the same page, what I am arguing is that the smooth features in the light curve, let me see if I can get the laser pointer. So the smooth features, spots, the sharp features, I think, need to be caused by clumps of gunk. And I'm going to argue that the composition of that gunk is at least including plasma, some partially ionized gas. I'm not yet sure whether or not we also need to invoke dust to explain this phenomenon. So I'll say that last part again. I'm going to argue I think I have evidence that these co-rotating clumps A exist, B include lots of plasma, but I'm not yet sure whether or not we need to invoke dust. Okay, what's the evidence for this picture? Basically, there's two lines of evidence. There's photometry, there's spectroscopy. On the photometric end, what's been really fun recently has been working with data from tests. Okay, just as a little bit of exercise for what you can do with the test data, I took the 2-minute data from 2018 to 2022, selected nearby bright kin M dwarfs, and ran a shape agnostic period search. Okay, that gives you a period at which there's a lot of power. What you can then do is write a little bit of code to count sharp local minima in those proposed periods. Okay, look at the objects, consider whether or not they would be part of this class. When you do that, you find a lot of interesting objects. Like I said, we now know of about 100 objects like this. About half of them were found in this recent study. Here's 25 of them. Here's the other 25. I'm not going to dwell. You can go look at them for yourself if you like. What I will say is that the sharp features from photometry are one of the important lines of evidence for the circumstellar material. You can't produce sharp, deep features like this with star spots. People have tried. What I would like to dwell on from the photometry has to do with how long these features exist. Okay, so what I'm going to show here is LP12502. This is one of my favorites. It's a 40 million year M4-ish spectral type. And what I'm going to show is data from June to December of 2022. And I'm going to advance a few cycles at a time. So at the beginning, there's 6 local minima per cycle with an 18-hour period. And when we advance, one of those dips just disappeared, and then it kind of grows back. These 3 on the left-hand side stick around for quite a while. There was actually a big jump there. There's a data gap, but they were persistent. These ones are evolving a little bit more. The upshot of staring at lots of movies like this is that the dips tend to last for months. However, sometimes they can collapse in less than 1 cycle. Often, though not always, those collapse events are triggered, or they seem to be associated with, stellar flaring. Now, that's interesting because in a picture where we have circumstellar material that's magnetically confined, stellar flaring means that you have a reconnection event, and perhaps, though I can't say for sure, perhaps the field lines are reconfiguring. You're freeing material to either flow out or perhaps accrete onto the star. It's a speculation, but it seems like this circumstellar material is influenced by the stellar magnetic fields. Now, what's nice about TESS, other than the light curve data that we get, is that TESS looks at bright stars. Bright stars mean you can do spectroscopy. So that's what I've been doing recently. The way to do this, I think, is by acquiring simultaneous photometry with the spectroscopy so that you know what are the dips doing during your spectroscopic time series. And what I'm going to show here is photometric data on the left from the Tierras photometer in Arizona. This is acquired by Juliana Garcia Mejia, who's at MIT now. And I'm going to show on the right the spectroscopy that we got from the Hale telescope in California. So we have just chromospheric emission in the Bouma lines, H alpha, beta, and gamma. And in the middle, I'm going to show the equivalent width time series of those lines. So just to prime you, if this circumstellar material, which I'm claiming exists, were entirely made of dust, you wouldn't expect it to do anything particularly notable in an equivalent width time series at these wavelengths, because dust doesn't preferentially emit or absorb at these wavelengths. So did we see a flat line? I would say no. In particular, in this photometric triple dip, which, by the way, this is actually over a couple stellar cycles between these 2 nights, so it's repeating, right? Orange and blue is repeating. The largest amplitude spectroscopic variability coincides with the largest amplitude photometric variability. I would love to have a detailed model to explain both. I don't have any models to show you today, but what I will say is that what we're seeing is an order of magnitude larger variability in the Bouma emission than in the continuum emission. And it seems like there's no way to do that with dust alone. You need to invoke circumstellar plasma. Okay, so that's, I think, a pretty good argument for why there needs to be plasma clumps in these systems. It would be nice, though, if you could say something a little more direct. And in particular, one way you might be able to do that is by taking high-resolution spectroscopy where you actually resolve the lines in velocity space. So I'm showing you a different star now. This one's TIC 1411, similar parameters as all of them, right? Young M dwarf. Period, though, a little different, 4 hours instead of 18 hours. This thing goes fast, V sin I, 130 kilometers a second. And In the middle, this is just the H alpha emission line, mostly chromospheric here, I think. And if I advance in time over the 5 hours of spectroscopy that we have, the line splits. And then it splits again. Okay? And what's kind of nice is that that emission is coherent. Okay? And the amplitude, the semi-amplitude of the signal, about 300 kilometers per second for one of these, 500 kilometers per second for the other. Okay, that tells you that you have plasma. It's moving around the star at up to 4 times the equatorial velocity in this case. Thank you. Okay, big picture. What have we learned? Why do we care? Well, I think the million-dollar question with these objects now isn't where does the circumstellar material come from necessarily, or actually, I should rephrase that. The big picture isn't, is there circumstellar material? Because I think we've shown that. The question is, where does it come from? Okay, this could be a purely stellar phenomenon. Some type of stellar prominence or wind might be trapped. It could be related to the youth of the systems. Perhaps there's an old and undetectable disk. There's no infrared excess, but that's just an upper limit on the dust mass. Or we know that rocky bodies are common around young M dwarfs. Perhaps those rocky bodies are hot. Perhaps they're producing debris that can then be charged and trapped. Okay, in such a scenario, this would be basically analogous to the Jupiter Io plasma torus. All of these are ideas at this point. We need more people to be thinking about these. We also need more people to be collecting data on these objects so that we can resolve these scenarios. Now, I'm just going to leave you with the 3 main points, and then I'd be happy to go to questions. The first point that I wanted to make is that these complex periodic variables are rare, but they might not be that rare. Okay, the second point is that the data, the photometry and the spectroscopy now require co-rotating circumstellar material. We're still trying to tease out the exact details of what that material is and where it comes from. And finally, I think in any of these scenarios, we're going to learn something new and exciting about the physics of the youngest and the coolest stars. Thank you.
We'll start with a question back here. Please tell us your name and your institution. There.
It's Rob Kaplan from Astro. Have you thought about the potential large-scale magnetic field that is probably directing these clumps, and how does this line up with, say, the geometry of the magnetic field? Comparing that to ZDI.
So I'll repeat the question. The question is, have I thought about the large-scale magnetic field, whether any ZDI data exists for these objects with which we might be able to infer the field, whether any radio observations have been taken? No, none of them have been taken. So it would be great if somebody looked at that.
I have a question. Can you tell me the distribution of the periods of these stars?
The periods more or less map onto the typical periods of young M dwarfs. So that distribution peaks roughly at, say, a day, and it's wide. There are lots of fast rotators that go down almost to breakup of just a few hours. There are also slow that go out to tens of days. The only important selection function for these objects relative to that M dwarf rotation period distribution is that they tend to be fast. So below 2 days, give or take. There are a few outliers, though, as long, perhaps even as 5 days. So I'll go ahead and repeat the question so that everybody can hear. Are these related to the prominences mapped out in AB Doradus by Andrew Collier-Cameron and collaborators in the late 80s and 90s? It seems like they are, because those emission features map very directly onto those prominences. However, those prominences were never observed to show broadband optical light curves with the same features. So there needs to be some new physics here that we're missing.
perspective from Florida. I was kind of curious about the last scenario. Why outgassing rock instead of something like, for example, evaporating hot Jupiter?
Rocks are more I'll repeat the question. Why an outgassing rock and not an evaporating hot Jupiter? It's simply because rocks are more common than gas giant planets. But both scenarios could be explored. Sure.
Thank you very much.
All right, does this work?
Yes.
I think it does. Amazing.
Right, we have David Conine, if I pronounced that right,
That's it. Okay.
from Astro.